Today I'm going to design a SKY65017 gain block PCB in Altium Designer. This amplifier can operate from 10 MHz all the way into the 5 GHz band while maintaining a relatively flat gain performance. It offers approximately 20 dB gain while it drops a bit in the higher frequency regions. Even so, it is a good low-cost wideband gain block for general amplification needs. The S22 performance degrades in the 5 GHz bands while the input return loss is still below -10 dB, which is quite good. The output return loss could be compensated by other means, but even then it is still a usable amplifier in the 5 GHz frequency region. The schematic is quite simple and taken from the reference design offered by Skyworks. It has a SMA edge connector on the input and output. Additionally, input DC blocking capacitor to prevent accidental DC input to the amplifier. This amplifier is biased using a bias T highlighted in the dotted yellow box. The C4 DC blocking capacitor ensures that no DC leaks out at the output port. The bias T is a mechanism that allows us to power the amplifier through the same port where it outputs amplified RF signal. The inductor L1 blocks the RF signal from being lost through the DC path, and the capacitor C4 blocks the DC from leaking into the output RF port. The inductor used as a value high enough to offer high impedance to the RF, thereby preventing it from taking that path. I have already prepared a board outline with 1 inch height and 1 inch width. First, I start placing the mechanical components such as the two SMA connectors. Both of them go on the two board edges, one on the left, one on the right. I already placed 4 mounting holes on 4 corners. Those will be used for in case I want to fit the PCB on a metal rack or some sort of mounting plate. Then I place other components like the SKY65017 chip and the bias T that is used to power the chip. It seems that I have made a mistake of swapping the pin 2 and 3 of the IC. The pin 2 needs to be shown as ground, but in the schematic I have shown the pin 3 and 4 as ground, so I need to fix the library. Meanwhile, I'll set the layer stack with 0.5 mm FR4 on the impedance profiles. I select the coplanar waveguide with clearance of 0.2 millimeters. Altium quickly calculates the necessary trace width that's shown. Coming back to our layout, you can see the corrected library part now shows the pin 2 as ground. Let's begin by setting the rules. First is the clearance rule of 0.2 mm that we need to maintain between the RF traces and between ground. So the RF traces were already added in the net class called CPWG, so it became quite easy to set the rules here. Moving ahead, we'll set the width constraint for the same net class. Rename it as width CPWG. We'll set the rules for the net class CPWG, and fortunately, being in a net class and having set the impedance profile in the layer stack, we were able to quickly set that constraint without much effort. Everything went effortlessly. So here I am routing the RF traces first. Those seem to be the critical traces in this board, which is relatively a simple board as compared to anything else. The power trace is slightly larger. Now, being a coplanar waveguide for RF, there needs to be ground all around it. So I place a huge polygon having the net connection to ground. I place the ground polygon on the top layer as well as the bottom layer. And now let's do the via stitching, via shielding. Basically, the via shielding will be for the RF traces. I'm just confirming whether the clearance constraints were applied correctly. Apparently they were applied, so no need to worry with the clearance. I select all the copper areas that need to be shielded. Go to tools, via stitching and via shielding, add via shielding, and I'll be adding via shielding to the selected objects, as you can see in the corner. Quickly adds necessary vias. You can obviously set the distance between two vias, the distance from the RF trace, which I have set to 0.2 mm because that's the constraint that we had set for the coplanar waveguide. Based on the data sheet reference design, we need to add a few vias around the ground pad here, which I am doing manually. Finally, I stitched the ground plane on the entire board using the same via stitching and shielding tool. Via stitching and shielding may not be very important at lower frequencies, for example up to 100 MHz or 500 MHz, but as you go up in the frequency, it becomes very important to have via shielding